The disk method is one of the methods that we have available that can tell us the volume of a three-dimensional solid of revolution. So here's how we get this solid of revolution before I show you the disk method. If you have a function, most of the time your functions are typically drawn in 2 dimensions, not 3 dimensions. So where does this function come from, or the solid come from in 3 dimensions? Well, here's what happens. We have a function, we'll call it f of x, and then it's spun around one of the axes. So for this example, I'm going to revolve it around the x-axis, but you could take another function and revolve it around the y-axis and get a different solid. But in this case, I'm going to revolve this guy around the x-axis. He's going to come out towards us. He's going to go down. He's going to go behind the xy plane and then back up again. And so after you rotate this guy around, here's what you'll start to see. Look, something kind of like this. So here's what it looks like halfway through the circle. Looks like it's halfway down, and then he's going to rotate back around and come up again. And when it's all said and done, it'll look something kind of like this. It'll have a circular end to it, right? A circular end to it, and some people will even do kind of like shading with it. That's not really necessary, but I mean you could if you wanted to. But anyways, you can kind of start to see this 3-dimensional shape here take place. This looks kind of like maybe like a vase turned on its side, you might say. And anyway, it has a particular volume, and so the goal of the disk method is to compute the volume of this solid here. So here's the disk method. Here's your formula for it. The volume will be equal to pi times the integral from a to b. And by the way, A is your starting point and B is your ending point from A to B of quantity f of x squared dx. Okay, kind of a strange little formula, but this is the guy you need to know. This is the guy you need to have memorized. This is what's known as the disk method. Now, where does this come from? That's a great question. I'll kind of go through some of the basics here in this video, but we'll get into some more of the details when we actually do an example or two. But let me go ahead and kind of illustrate where this formula is coming from, and that'll really help you memorize it. To be honest with you, you can memorize it easier if you understand where these pieces are coming from. Well, if you take an approach similar to how we did with Riemann sums, when we're finding the area under a curve and we broke it up into rectangles right throughout the interval, we're going to do the same thing here. If we took a sharp knife and we cut this guy in 2 places, let's say like here and here, and took a cross section of this or cut a little slice out, you'll notice this guy right here would look like a disc, right? Because it's got a circular face to it with a certain amount of depth to it. So it looks something like this if we cut it out. This drawing may not be the best, but you get the idea. Okay, so let's say that's a disc, and let's remind ourselves, what was the volume of a disc? Think like high school geometry. Well, it depends on the radius of the disc, and it depends on how wide it is. We'll call it delta x. So this guy's volume for this single disc would be pi r squared, that's the area of one of the faces, times delta x. That's how deep it is. And so you see remnants of that in this integral here. Here's a pi. Delta x is coming from dx. Let me change the colors here so you can see them a little better. The pi is, thought I changed colors. Let's try that again. There we go. The pi is here. The delta x turns into your dx, and this is probably the only confusing part of the change over here. This was supposed to be r squared, but I've got f of x squared. So why is it f of x? Well, if you look back at the solid here, notice how every disk radius is not the same. Where I have it, I have somewhat of a small radius, but if you look somewhere else, another disk might have a large radius or something in between. And so you'll notice that the radius changes depending on where you are on the x-axis. In other words, it's a function of x, and specifically the radius is f of x because the radius is stretching out as far as the curve goes. And so for your radius, which is always changing, you're going to write f of x. And so we see remnants of this volume of a disk in our disk method. Now there is some more details to it than that, but this right here should be enough just to get you started and help you remember just the basic format of the disk method. You can find some videos with some examples on the disk method at my website, fireflylectures.com. So I hope you'll check those out. And if you want to stick around for about 30 more seconds, I'll go a level deeper and explain on a deeper level where this is coming from as well. So here we go. Let me hide this here real quickly. Let me bring this layer up here. Where the disk method is coming from on a deeper level is actually very similar to how we did Riemann sums and how Riemann sums converted into a definite integral when we were talking about area. You'll remember this little part right here was called a Riemann sum, and that approximated the area under the curve. And what we did was we took a rectangle, width times height, right? Width times height, and then we did that for multiple rectangles, and then we added those areas up. Now, to make that approximation converge to the actual area under the curve, we took more and more rectangles. In other words, we took the limit as the number of rectangles went to infinity. And so that approximation got better and better, and it converged to what we call a definite integral, and that's your exact area under the curve. We're very comfortable with that. Now, what we're going to do is something identical to that. We're going to take not just one disk, but a lot of disk, which was pi r squared delta x, pi r squared delta x. This right here was one disk. We'll add those up. That'll be an approximation to the volume of the solid. And then we'll take finer and finer disk, in other words, more and more disk, and let that number of disk run on to infinity. And that approximation again will converge to the exact volume. And so just, follow the pattern. Follow the pattern from when we did Riemann sums and it converted into a definite integral. You're going to get the same things. You're going to get a pi. You're going to get f of x squared dx with a definite integral from a to b. So there's possibly a little bit more we could say, but that should at least get you a pretty clear picture as to where the disk method is coming from. So again, check out some more of these videos at fireflylectures.com, and you'll find a link to that website in the description.